Welcome back, folks. This is the fourth segment of section 6.1. I'm thinking we might possibly be able to get this done in one go, but we may have to actually come back for a fifth segment as well. So let's just get right to it. What we're going to be looking at now is we're going to compose functions of one kind or another that aren't identical. So what we've seen before is we've seen situations where it's like this sine of an inverse sine, or cosine, inverse cosine of a cosine, or whatever, where the function has been the same. But what I'd like to look at now is a situation kind of like this one, where we have, for example, say secant of the inverse cosine of the square root of 2 over 2. Now this is where we're starting to use some things that are just a little bit different than what we had before, but it's going to come down to the same basic strategies for now. We're going to see some stuff that actually gets pretty crazy. So the first thing that we'll do is anytime we can evaluate something, it makes sense to do that. So the inverse cosine of square root of 2 over 2, remember the range on inverse cosine is from 0 to pi. This is a quadrant 1 angle, and a reference angle is pi over 4. So this becomes secant of pi over 4, which is pretty easy to evaluate. That's just square root of 2. Okay? So far, so good. Let's mix it up where it's not maybe something, how about something like this? How about the cosine of the inverse sine of square root of 3 over 2? Okay, well, same sort of situation here. We're just going to evaluate this term. Now, inverse sine of square root of 3 over 2, that's going to be an angle in quadrant 1, and its value is pi over 3, right? So then the cosine of pi over 3 is going to give you 1/2, right? So far, so good. We could do a couple more like this, but let's give it a couple more. So how about the inverse cosine of the sine of pi? This is kind of reversed. Here we had trig function of an inverse trig function of an inverse trig function of known value. So what we get from here, okay, so sine of pi is 0. So this becomes inverse cosine of 0. Now this is going to be, where does cosine equal 0? Well, it equals 0 at 90 degrees, or pi over 2, right? And that's in the range of inverse cosine. Let's try maybe couple more like this. Let's do the inverse sine of the cosine of 3 pi over 4. Well, when we can evaluate things, that's what we want to do. So the cosine of 3 pi over 4, well, that's an angle in quadrant 2, and so it's going to be negative. It'll be negative root 2 over 2. So it becomes inverse sine of negative root 2 over 2. Now we know that the inverse sine has a range that's quadrant 4, quadrant 1. So between negative pi over 2 to positive pi over 2. This is going to be an angle in quadrant 4, and it's going to have a numeric value equal to minus pi over 4. Let's do one involving maybe like a tangent in there or something. Where it's a known value, and then we'll get to some that are a little bit more challenging. So let's take the inverse sine of the tangent of negative pi over 4. Okay, well, sorry. I think my document camera is not looking in the right place. So much. Do a little adjustment there. Okay, so we're going to evaluate this tangent term. This is going to be, well, this is a known value, so this is going to be -1. So we have the inverse sine of -1. Well, this is in the range of inverse sine, or in the domain of inverse sine. So where does it happen? It actually happens at -pi/2. Okay? So those, like I said, those are some pretty easy versions of the kinds of things where we have composition of different kinds of trig functions, which, you know, those are, like I said, those are really the easy ones. Here's where things start to get a little bit interesting. Okay, so let's look at this one. How about the cosine of the inverse tangent of square root of 3/4? Okay, so now this doesn't have a known value. I don't know what, and we need to have and all of these will have exact answers, right? But I don't know what the angle is that's associated with the tangent being square root of 3/4. I really don't know what it is, but I know that it's an angle in quadrant 1. So how about I maybe draw it and label what I do know. So this tells me what y is and what x is. So there's some point out there that has a x value of 4 and a y value square root of 3, and the r value will be the square root of 16 plus 3, which will be square root of 19, right? That's just x squared plus y squared, take the square root. Okay, so it turns out that for most of these compositions, you end up doing this a lot. You have to draw this angle and then say, okay, well, what's the value? So consider this. Inverse tangent of square root of 3/4. That's this angle, right? It's that angle. And when I take the cosine of that angle, it's just simply going to be x over r, right? So there's my x and there's my r. This is going to reduce down to 4 over square root of 19, which when I normalize it, root 19 over root 19 is going to be 4 root 19 over 19. Okay, seems like a weird way to do it, but you know, those skills that we developed in chapter 1 and chapter 2, this is where they start to get applied. And you're thinking, well, why in the world would I be taking the cosine of an inverse tangent? Well, it'll come up. So let's look at another example where we have to use a trigonometric identity. These do happen from time to time, and then we still have to do kind of the same stuff. So this is actually going to be a little bit of a long problem. So I think I might have space here for it, but let's state it and see what we've got here. So cosine of the quantity 2 times the arc sine of 1/4. Okay, this is a deceptively difficult problem. And let me just start with this observation. What you have right here is an angle, right? Inverse sine of 1/4. I don't know what the angle is. It's an angle in quadrant 1, but there it is. And this 2 means that we now have a double angle, right? So what do we do with double angles? Well, if it's cosine of 2 theta, we would bust that into one of the 3 versions of cosine of 2 theta, right? Now, I don't really know which one to pick, but I'm going to pick the one that's probably the least, the wrong one to pick, which is just the first one. So note that cosine of 2 theta is going to be equal to cosine squared of theta, which is the arc sine of 1/4, minus sine squared of the angle, which is arc sine of 1/4, right? Now, the first term over here is pretty easy to evaluate, right? Because it's going to be sine of an inverse sine. Remember what I said about trig function of an inverse trig function is always just going to give you the ratio out, or it's going to be undefined. Well, in this particular case, this works perfectly well. And so the sine of the inverse sine of 1 over 4 becomes just simply 1 over 4. So this is 1 over 4, and don't forget that it's squared. Okay, so over here though, this is kind of a whole different problem, because here we're wanting to take the cosine of an inverse sine of something that we just don't happen to know what it is. So I'm going to take a minute here and draw this angle. Again, this is an angle in quadrant 1. So let me draw an angle in quadrant 1. And the values here, that the y value, there is some point on this ray where the y value is 1 and the r value is 4. So how do I find the x value? Well, the x value is going to be the square root of 16 minus 1. That's r squared minus y squared. And it is going to be positive because it's a quadrant 1 angle. This reduces down to square root of 15. So what's the cosine of this angle? I mean, that's what this is saying. Cosine of that angle, right? The cosine of that angle is going to be x over r. So we have square root of 15 over 4, and then don't forget that it's squared, right? So that makes it a little bit cleaner. So the net result here is that we're going to get, when we square these, we get 15 over 16 minus 1 over 16, which equals 14 over 16, which happens to be 7 over 8. Okay? Kind of a long-winded problem there. And of course, they can get a little bit weirder. Let me try one that involves, now this one involved a double angle. And can you tell which, I mean, hopefully you can tell which version I should have used. I used the cosine squared minus sine squared, which made me have to do so much more work. But I probably should have used the version that's 1 minus 2 sine squared, because I wouldn't have had to do very much at all. But I wanted to illustrate how to actually tackle those. So let's try one that maybe looks a little bit different. Let me get another sheet, because this is kind of the stuff that people usually have a lot of problems with, because what they want to do is they want to just take that 2 and dump it out. And of course, we've spent all this time saying you can't do that. So anyways, so I believe I'm on page 11. Let's look at this problem. How about we take a difference? So let's take the, how about we find the sine of the inverse tangent of 4 over 3 minus the inverse tangent of 12 over 13. Okay, now again, I don't know this exact value, but this is definitely an angle, and that's definitely an angle, and it's a difference between two angles. So I have sine of A minus B, where this angle is A and that angle is B. So recalling the sine A minus B formula, it's going to be sine of the first angle, which is inverse tangent of 4 over 3, times the cosine of the second angle, which is the inverse tangent of 12 over 13, minus, and I'm going to have to bring it down to the next line, the sine of the second angle, which is inverse tangent of 12 over 13, times the cosine of the first angle, which is inverse tangent of 4 over 3. Okay, now this is starting to look really messy, but all we have to do is really draw two angles. So we're going to draw the diagram for this angle, and then the diagram for that angle. Whoops, I missed a parentheses. We're going to figure out x, y, and r for both of these, and then we can just start substituting those values. So the first triangle, or sorry, the first angle is this one where inverse tangent of 4 over 3. Well, that means that it's an angle in quadrant 1 that has a y value of 4 and an x value of 3. And we've seen this enough times that you'll find out pretty quickly that r is equal to 5. Okay? Now this other one, this 12 over 13, inverse tangent of 12 over 13, that's a different angle, but it's still in quadrant 1. And there is a point out here on the terminal ray that has a y value of 12 and a x value of 13. Now it turns out that this is going to be something ugly, but let's just see. So r is going to be equal to the square root of 12 squared plus 13 squared, which is square root of 144 plus 169. And I think that comes out to 305. No, 303. 313? Yeah, okay. Not anything awesome, but that's definitely the R value. Okay, so let's look back at these. Let's look back at these triangles. We have X, Y, and R for this is that first angle, and here we have X, Y, and R for the second angle. So what's the sine of this angle? Well, that's just going to be Y over R, right? So I'm going to kind of draw some lines here. This sine of this angle is going to give us y over r, which is 4 over 5. That's the first term. The next term is going to be the cosine of this angle, which is x over r, which is simply going to be 13 over square root 313. We'll get this cleaned up here in a minute. And then subtract, wish I'd started a little bit lower, subtract the sine of this angle, which is going to be 12 over the square root of 313, times the cosine of the first angle, which is just going to be 3 over 5. Okay, so now we kind of clean these things up, because we've got this numerator is going to be 42 over 5 square root of 313 minus 36 over the same denominator. Turns out that pretty much always happens. You end up with the same denominators in these things. But this is going to be, what, 6 over 5 square root of 313. 313 is probably a prime number. I'm just kind of guessing there. But I'll go ahead and simplify, rationalizing the denominator. And then what we're left with here in total is 6 square root of 313, and then it's over 5 times whatever 5 times 313, which is like 1,565, I think. I might check my arithmetic there, but I think that's the solution. And you could check it. You could go take a calculator and plug these numbers in and take sine and see if this is the answer you get. But this is kind of the hardest sort of problem that you'll ever see from this section. But I do want to point out one other kind of problem, which is where we start seeing, instead of numbers in these arguments, we will start to see variables. Okay, so let's take a look at one that's relatively simple. I've got 3 here that I want to look at. They get progressively harder. So section 6.1, this is page 12 now. Okay, and we want to write the special instructions here are that x is a variable greater than 0. So for every one of these, x is going to be a number that's a positive number, which helps because then we don't have to write a bunch of piecewise functions. But let's take the tangent of the inverse cosine of 3 over x. So now we're starting to see variables, right? But this doesn't really change anything. I mean, we're still going to take, this is some angle that I don't know what it is, but I'm going to draw it. It's an angle in quadrant 1 because x is positive. It has a x value. This is weird, right? The x coordinate is 3, and the r value is x, right? So cosine would be 3 over x. So now I just need to find out what the y value is. Well, the y value is going to be what? It's going to be x squared. Y squared is going to be x squared plus 9. So y will be the square root of x squared plus 9. Okay, and so when I take the tangent of this angle, it's going to be y over x. So this reduces down to just square root of x squared plus 9 all over 3. Kind of a goofy looking thing. Maybe another one that's kind of simple like this. Let's take the sine of the inverse cosine of x. And again, x is a positive number, so it's going to be represented by an angle in quadrant 1, inverse cosine. And in this case, it actually works out pretty well because this is x over 1, right? So that tells us that the x coordinate is in fact x, which is nice, and r is equal to 1. But then that makes the y value up here, it's going to be the it's going to be the square root of 1 minus x squared, right? And so the sine of this angle is y over r, which happens to just be the square root of 1 minus x squared. Kind of tricky, huh? Okay, so let's try one more like this, and then we're going to call it quits. I think this video might be running long, but this is the last problem for section 6.1. So let's take a look at the tangent of the inverse secant of some bizarro thing, square root of 9 plus x squared all over x. Okay, so again, I don't really know what this is, so I'm going to end up drawing an angle in quadrant 1 because everything here is positive. And notice secant is not x over r, it's actually r over x. So what this is telling us, this is the r and that's the x. Again, we have an x coordinate whose value is x, which is just fantastic. R is equal to the square root of 9 plus x squared. Okay, so how do we find y? Well, notice r is y squared plus x squared is another thing. So we already know that y squared is 9, so y must be 3. A little bit of quick manipulation there to get that. So this diagram represents this angle. And that's kind of the key, is that you got to remember this is an angle, and the information that we're being told about is the ratio. As long as you know which quadrant it's in, you can draw it, and then you can start saying, well, if you want to take a trig function of this angle, we know how to do that, right? You just take a tangent of whatever this is y over x. So this will reduce down to just 3 over x. Okay, so this is the end of section 6.1. I'll have all these documents up on, I've got a new scanning program for my phone, which maybe will make these things a little bit cleaner. I'm going to try that out here, but we'll be back in section 6.2.